Hey Chem 20s, welcome to another lesson with Mr. Jukley. Today we are jumping into chapter 6. It's the second part of our solutions unit and it's all about acids and bases. So something kind of weird happened in the workbook here where well, it was originally 2 workbooks. So the numbers start over. We are on page 1, but it is the second page 1 in our workbook. So just find the spot. It's a little more than halfway through. That was not a pen at all. A little bit more than halfway through, and we'll get going from here. So let's see. We'll use that color today. Cool. So the first little bit of this is going to be a ton of review, lots and lots of review, and big ideas on acids and bases, and then we're going to get into something called the modified Arrhenius theory of acids and bases, which is sort of the next level from what we already know for acids and bases. Oddly enough, there is another level in physics, or not physics, sorry, Chem 30, which is the Bronsted-Lowry version, but we're working up to that, working up to it. Cool. So, first little bit, acids and bases are everywhere in our lives. They're all over the place, all over the place. So, a couple acids, and by a couple I mean really very few out of the hundreds and hundreds of acids that we encounter every day in our life. We've got vinegar, which is ethanoic or acetic acid. We've got wart remover, I can't talk today, salicylic acid. There we go, finally got it out. Soft drinks that contain carbonic and phosphoric acid, rust remover, glycolic and phosphoric acid, lemon juice, citric and ascorbic acid. So just a couple of things that we see all the time. And then bases, right? Like one of the things that you note, what do you notice about bases here? Cleaner, cleaner, cleaner. Lots and lots and lots and lots of cleaners are basic. So let's even have a look over here. So let's see, oven cleaner. Sodium hydroxide, we recognize that one because remember our old version bases contained OH negative, right? Acids contained H plus, bases contain OH negative. That's our old version. We're learning new stuff today. Okay, cool. Sodium hydroxide, magnesium hydroxide. Hey, wait a second. Why is ammonia a base? There's no OH in that. What the heck? We're going to have to look at that a little bit more. Okay. Another thing to look at here is a review of naming acids, because the whole entire chapter is about acids and bases. We should definitely review how to name those acids and bases. So as I go through and as I review this, we've got 3 different endings. So hydrogen something ide, ate, and ite. Notice for now they all start with hydrogen. So if I had hydrogen blank ide. For example, if I look down at the bottom here, H2S, that would be hydrogen sulfide. What I would do is I'd drop the gen and I'd call it hydro sulfuric acid. So changing that ending, we're dropping the hydrogen, we're dropping the gen part and just calling it hydrosulfuric acid. So again, we've looked at that quite a bit before. I'll leave you to review it on your own. You can always look back at other videos. I'm sure there's tons of videos on YouTube about naming acids and bases. Next one that we have is ate. So when I see 8, so hydrogen something 8, I automatically think polyatomic ion. Same thing with ite. So these two are both for polyatomic ions. And if I have something that ends in 8, I drop the hydro entirely and just change the ending to ic acid. So for example, down here I've got HCO3, which is hydrogen carbonate. So I ditch the entire hydrogen, that is entirely gone, and change the last little bit to ic. So carbonic acid. Cool, okay. And then finally, the back to the pen there. The last one is with ite. So if I ever see an ite ending, for example, hydrogen chloride, I totally drop the hydrogen again. Hydrogen is gone, and I change that last little bit to us, O-U-S. So chlorous acid. Cool. Again, depending on where you're at with this, you might want to do a bit more work. You might want to go back into some of that review we had way at the beginning of the year and look at naming acids and bases. You might want to just even look up a quick video to refresh your mind. But yeah, oh, and I may have gone a little fast there. Nope, Nope, that was good. Okay, so empirical definitions of acids and bases. So empirical is just stuff that's easy to see and experience. So many solutions that are acid, basic, or neutral, they all look the same. A lot of them are clear colorless solutions. So there's other definitions and other things we have to look at. You probably remember that acids make aqueous solutions and they neutralize bases. So fairly straightforward. They're typically colorless. They turn blue litmus paper red, and red litmus paper stays red. Acids are electrolytes, so they conduct electricity, some more than others, but they all conduct at least a little bit of electricity. They taste sour. Just think about lemon juice with that one. And then typically acids react with metals. So metals like zinc, magnesium, and they produce hydrogen gas. I don't know if we actually made a hydrogen balloon and popped it in our class. Shoot, that's one thing we might have missed out on. Anyways, know those properties of acids. Bases, when they form aqueous solutions, well, when I talk about bases, they neutralize, or at least partially neutralize acids. They also form colorless solutions. They turn red litmus paper blue, or blue litmus paper stays blue. They are electrolytes, so in other words, they conduct electricity. They typically feel slippery to the touch, and they typically taste bitter. So last time you had your mouth washed out with soap for having foul language, well, soap's a bit of a base. You now know why it tastes so bitter and awful. Also, no swearing. Okay, neutral solutions. Well, these are kind of all over the place because there's a lot of neutral solutions. They could form colored or colorless solutions. They could be ionic or molecular. They could, well, they don't affect litmus paper, so red stays red, blue stays blue. If they're molecular, they're non-electrolytes. They do not conduct electricity. If they're ionic, they are electrolytes and they do conduct electricity. Cool, so lots of review here, right? Lots and lots and lots and lots of review. So last little piece to kind of go through on this page before we flip forward is diagnostic tests that you can do. So again, differentiating between molecular, ionic compounds, acids, and bases. So things that we want to look at, important things are conductivity. So if you're ever testing like say 4 different substances and you find out that one of them is a non-conductor, it is a non-electrolyte, well, chances are that's a molecular compound. If you go through and test with litmus, so litmus is this column over here. Neutral compounds, so most molecular and most ionic compounds, they don't have any effect, which means that their pH value, and we'll do a bunch of work with pH, is 7. Whereas acids, well, they turn litmus paper red and they have a pH less than 7. Bases turn litmus paper blue and they have a pH more than 7. Maybe we should take a moment just to look at this pH scale. So 7 is neutral. So you probably remember this. And then anything above 7, and we typically go up to 14, but you can actually go higher than 14, is a base. And the further you go towards 14, the stronger the base. When we go the other direction, we go down to 1, and typically we stop at 1, although you can have less than 1. But they're acids if they are less than 7, and then again, the stronger you go to that one side of things, the further you go to that one side of things, the stronger acids they are. Next piece that we want to check out here is just it's been a long time since people were trying to figure out acids and bases. So since around 17th century, at least for the litmus, people had a really hard time explaining acids and bases and exactly how their unique behavior happens. So I'm kind of going to leave this for the most part. If you want to read that, that's good. Things that we want to check out are the Arrhenius. So that's the one that we've learned before. Acids make H+, bases make hydroxide ions and have to have hydroxide ions. What we're kind of going to look at, Paul Giguère, I believe that's how you say his name, actually took our Arrhenius, that's the one, again, the one that we know about, and took it one step further, and we're going to call it the modified Arrhenius version of acids and bases. And yeah, that's our big thing. That's what we're jumping into right away here. So again, just kind of to reiterate, I went through that very, very quickly. Our Arrhenius explanation for acids and bases is essentially talking about some substances dissociate and will conduct electricity. Both acids and bases do this. Arrhenius proposed, and in the box here's the big thing, that a substance ionizes in water to form hydrogen ion. Now that's kind of a weird thing because, well, how does something ionize? We're not calling it dissociation because it's not really dissociating. Only ionic compounds do that. It ionizes. It goes from a molecular compound. So HBr is a molecular compound, and somehow it forms ions. Doesn't really make the most sense when you think about it like that. But that's what he came up with, and that's what most people actually know acids as. And only if you take Chem 20 and 30 you start to see more details and bigger ideas with this one. Okay, Arrhenius also said that bases dissociate in water to form hydroxides. Now we think about what that means. Dissociate are only for ionic compounds, so it has to be an ionic compound and it has to contain, so with hydroxide ions built into that ionic compound. And then we see the barium hydroxide example here. Barium hydroxide breaks apart into barium, and oh, look, there it is. That's that hydroxide ion that tells us that it is a base. So yeah, that's essentially where we're at. So as you increase the number of H plus or hydrogen ions, you become more acidic. As you increase the amount of hydroxide, you become more basic. And again, we ionize to make hydrogen. We dissociate to make hydroxide for bases. Cool. Again, we've already run into one or two little issues here with that. One, like how do things ionize? That doesn't make a ton of sense. So one of the things that we kind of missed out on here in this format of learning that we're in right now is we never actually got an opportunity to go into the lab and test which things are acids and which things are bases, acids and bases. So I'll give you a couple quick examples here. Carbon dioxide, CO2. When that dissolves in water, is it an acid or is it a base? And if we're looking at that Arrhenius version, well, we can't really tell, right? Because there's no H plus and there's no H negative. But I'm going to tell you right now, carbon dioxide, when it's dissolved in water, forms an acid. And then NH3. You might look at NH3 and be like, oh, wow, look at all those hydrogens. Oh, it's got to form absolutely got to form an acid. It doesn't. It doesn't. It actually forms a base. Right, so that's kind of a weird thing, right? Because those definitely don't follow our Arrhenius rules. So that's why we're looking at the modified Arrhenius theory of acids and bases. And here is the whole key with this, the really, really, really big idea. Acids, they no longer ionize. Acids will react with water in all cases to produce, let me finish writing it or I'm going to start making spelling mistakes. React with water to produce hydronium ions, H3O plus aqueous. And then I'll put it in brackets. It is hydronium ions. So some of the good stuff about this, right, is now we're looking at this and we're saying, okay, it's not just magically ionizing, creating this H plus, this hydrogen ion that's ridiculously unstable all by itself from a molecular compound. We're saying it's reacting with water, and absolutely there is a transfer of hydrogen of H plus, but now that H plus is clinging on to the water molecule to make that H3O. Cool, so they are now reacting with water to produce H3O. Cool, that's acids. When I look at bases, we've sort of got two things for bases. We've still got ionic compounds with hydroxide ions, so that's still one thing, and they obviously dissociate to make I'm going to do X because there is no element X. So some sort of positive and OH negative. And again, X is just whatever random positive that's out there. It could be, sodium, it could be magnesium, it could be anything, just whatever cation that we've got there. So a cation and OH negative. So that's one thing. Cool. That's typically what we call our strong bases, actually, which we'll get to a little bit later in the course here. But ionic compounds that dissolve really well to form OH. The other thing, like that ammonia, the NH3 that we just talked about, bases also react or can react with water to produce. You're never going to guess what they produce. Yeah, hydroxide ions. You might have guessed it, to be totally honest with you. They react with water to produce hydroxide ions. So they produce those hydroxide. It's still all about hydroxide. It's just now sometimes you don't actually see that hydroxide in the compound. Again, for example, I'm just going to write this off to the side, NH3, where the heck is the hydroxide? That's going to have to react with water to produce OH negative. Cool. All right. So let's go through a summary of how on earth we want to do this. So we want to first write the chemical formulas for the reactants. So we want to have polyatomic ions plus water, essentially. Now when we're doing this, we want to really dissociate any ionic compounds. Right? Because that's what we're really looking for. So write the formulas for the reactants, the things that are actually going to react with water to produce, if it's a base, hydronium, if it's a, sorry, I said that backwards. If it's a base, hydroxide, if it's an acid, hydronium. Cool, so write those out. What we do with this is you can pretty much ignore every single thing in group 1, 2, and 7, except for fluoride. Fluoride's a little exception in there. So just ignore it. If you see it's in group 1, if you see it's in group 2, if you see it in group 7, pretty much ignore it. It's not going to form an acid or a base whatsoever, and that comes from lots and lots and lots and lots of evidence. If it is a non-metal oxide, so what we mean by that is a non-metal oxide. So that's something that ends in oxygen and starts with a non-metal. So like carbon dioxide, sulfur dioxide, nitrogen dioxide, and on and on and on. Or even if it's a metallic oxide, like BaO, they're going to involve 2 steps where they react with water. 2 steps reacting with water. And I'll show you all this in a second here. So we want to note the evidence provided. Oftentimes it's going to go ahead and it's going to tell us, okay, this one's going to make an acid, this one's going to make a base. If it tells you that, just write out, if it makes an acid, one of your products is going to be hydronium ion. If it makes a base, one of them is going to be hydroxide ions. We're going to be able to take this one step further actually here. We want to figure out and we want to see and be able to predict which ones are going to form acids and which ones are going to form bases. Now sometimes that's just about impossible, but sometimes it could be one, or it could be the other, or it could potentially be both. And we'll look at that as we go through. Okay, so we want to complete the other products by figuring out whatever atoms are left realistically, and the charge required to balance the equation. So if I had a charge, let's say, of +1 on my reactants, I need a charge of +1 on my products, and vice versa. If it's +2 on my reactants, I need +2 on my products. So we're balancing not only the charges, but we're balancing the atoms as well. Again, we'll show you this in a second. And then finally, and almost one of the most important things, when we're figuring out the other product, so not the hydronium, not the hydroxide, the other product should be recognizable. So usually a polyatomic ion or something that you've seen before at least. We'll look at examples of that as we go through. Cool, so that's a lot. Let's check it out here and let's see what we can find. So example number 1, I've got HBr, and it doesn't tell me if it's going to be an acid or a base, but I know that it's going to react with water. H2O liquid. And I'm being kind of lazy here. I didn't put states in, so let's go ahead and put some states in there. So with this one, as I go through, my options are, and maybe don't write this out yet, my options are going to be either OH negative, and that's where one of the two hydrogens was stolen and given to the other thing, right? And it's all about stealing or giving hydrogens is realistically what we're looking at. So I could do OH negative, right? And then if that hydrogen, so one of those two hydrogens goes from the H2O and goes over to here, remember the hydrogen is going to carry a positive charge. It's going to form plus H2Br plus. Okay. Now let's check and see if we've done this right. OH negative. Is that reasonable? That one's okay. H2Br plus. What? That's not a thing. It's not a polyatomic ion. It's not even realistic. Like if H has a charge of plus and Br's got a charge of -1, there's no way we're ever going to get those. Okay, so that is junk. That's not going to work out for us. So let's erase that and let's try it the other way and see if the other way makes sense. So we tried it as a base. Let's try it as an acid. So acids are going to produce H3O. Okay, I got to erase this little bit here as well. Okay, so go back to my felt pen. There we go. So the hydrogen did not go this way from the water to the other compound. So maybe the hydrogen goes this way. So the H plus, instead of being given from the water, maybe the water's taking it. Right? So instead of H2O, now we got H3O. What's the other thing on there? Br negative. Remember, because the H is a charge of +1. And this, I think, now makes sense, right? Because we've seen bromide ions before. And we haven't seen much of it, but we've seen H3O. So this is what we're looking at. So this one is good, and this one is indeed an acid. Cool, that one is an acid. Hey, the next one, NH3, we already said that one's a base. Let's go through it. I'm going to do it wrong to start anyways, just to see what I was talking about, and I know it's going to be base. So I got NH3 aqueous plus H2O, and then let's pretend that I said, okay, and this is going to be wrong. I'm going to do it in red, and I'm going to erase it because it's definitely going to be wrong. Let's pretend, let's go through and say, oh, I see 3 hydrogens here. Maybe one of those hydrogens is going to be given to the water, and it's going to produce H3O. Again, this is totally wrong. It's not going to happen. What would I be left with? I'd be left with NH2 with a charge of 2 negative. What on earth is NH2 with a charge of 2 negative? It's not a polyatomic ion. It's not something we've ever seen before in all of the chemistry that we've done. That's how I know that I'm doing this one wrong, right? The other thing should be recognizable. Okay, let's try to do this the right way now. This is the right way. So I've done it the wrong way. I know that NH whatever, 2 or whatever I said isn't there. Let's try it the other way. In this case, I'm going to give one of those hydrogens from the water over to the NH3. And in that case, it would form OH negative, absolutely recognizable from a base, and it would form NH4 positive. Now, have we seen NH4 before? Absolutely, we've seen NH4. No problem. That is good to go. NH4 is ammonium ion. And let's see, back to my original felt pen there. This one is going to form a base. Cool. I hope we're getting the idea of this one here. Hope we're getting the idea. Couple more examples. I just got 3 more examples. Let me just do a quick check of the timing here. Holy, it's getting pretty long. If you need to take a little break, feel free to pause the video and come back at any point in time. But 3 more examples before we get you to go with a bit of practice. Okay, so Na2CO3. Hey, that sounds like one of those weird ones where we've got a oxide, a non-metallic oxide, or at least something like that. So my very, very first step is I'm actually going to take this compound and I'm going to dissociate it. So it's going to dissociate into Na plus, technically 2 Na pluses, and CO3 2 negative. Okay, now back to those original rules. Should we do anything with anything in group 1? Right, so sodium being in group 1, I'm going to get rid of that. I'm going to cross that off. We don't do anything with sodium in group 1. Cool. So that means it all comes down to the carbonate ion, the CO3. So I got CO3, 2 negative, and I'm going to go through and I'm going to say, okay, CO3, 2 negative. I'm going to react that with water, H2O, which is a liquid. Oh, I forgot lazy on that one. Liquid. Of course, that one's aqueous. And then I'm going to go through and I'm going to say, okay, well, CO3 doesn't even have any hydrogens to give up. So there's only real one way that this could go. The hydrogen could be given to the CO3, to the carbonate ion. It can't go the other way because the carbonate doesn't have any hydrogens. It's all about the transfer of hydrogens. So that means I'm going to have OH negative, aqueous, cool, because the water, the H2O, gave away one of its hydrogens. Now it's just OH negative. And then if it gave it to one of the other things, it's going to be CO3, but I added that hydrogen to it. Remember, the hydrogen charge comes with a charge of +1. So instead of being 2 negative, this whole thing is now only going to be 1 negative. And of course, we need to include the state. I don't think I checked this on the previous ones either. So what's the overall negative charge in the reactants? So I got, let's see, maybe highlight it in green. Over here, I've got -2 plus 0. And over here, I've got -1 and -1. So that's -2. -2 equals -2. The math checks out. Perfect. So then looking at Na2CO3 sodium carbonate, is that an acid or is that a base? It's a base. Nice. Oh wait, I might have got ahead of myself on that one there. It's not really one of those non-metallic oxides. D is one of those non-metallic oxides. So when I look at D, it's carbon dioxide. Excuse me. This is going to take 2 steps to do, and this one's a big one because we haven't really looked at it yet. I'm just going to clean this up a little bit up top there. So first step is I'm just going to combine carbon dioxide and water in my chemical reaction. I don't know why that O is so small. Carbon dioxide and water combined in my chemical reaction. So liquid, and this one's going to be aqueous, kind of small and messy there. Cool. Now if I were to jam this all together, I've got 2 hydrogens, H2, I got 1 carbon, and how many oxygens do I have there? 3 of them, H2CO3, aqueous. There we go. So we just jam the water together with that non-metallic oxide. Very good. Jam it together. And again, it should be something recognizable, right? I'm sure we've seen H2CO3 before. Now the second step is I'm going to take that H2CO3 and that's what I'm going to react with my water, H2O liquid. And of course that one is aqueous. Need a bit of a skinnier felt pen almost for this. Aqueous, there we go. That'll be a little bit nicer. So, going and figuring this one out, you could probably already start to tell my H2CO3, well, it's got some extra hydrogens out front there. Extra hydrogens in front typically tell us it's going to be an acid. We could pretend that we're going to go the other way. If a hydrogen were to go this way, I'd end up with H3CO3 negative, which is not a thing. Definitely not a thing. So I think what's going to happen with this is the H plus is going to be transferred to the H2O. It's going to make H3O. And then let's see. The hydrogen carbonate just lost one. So instead of H2CO3, I think it's going to be HCO3 aqueous. And its charge is now going to be not +1, it just lost a positive. If it loses a positive, means it's going to be a negative, HCO3 negative. Cool, and that's recognizable, HCO3 negative. Perfect. Okay, the next one's a bit of a doozy here. I don't know if I'm going to have enough space for this one, to be totally honest with you. I'm going to get an even thinner felt pen somehow. even thinner, the thinnest felt pen that the smartboard will allow me to have. So first step with this one is I'm going to do a dissociation equation. I'm going to break it up. I'm going to erase the stuff that's right above this as well. So if you needed to pause or anything or rewind, it's the beauty of a YouTube video, you can always do that. I'm just going to make a line across so that I've got loads of space to work with here. Okay, so first step, NaHSO3 aqueous. And I'm just going to dissociate that. It's going to turn into Na plus and HSO3 or 4, shoot, 3 negative aqueous. So I think I made a little screw up there. It's HSO3 rather than HSO4. Perfect. So that's just our dissociation equation. You'll notice everything still balances, including the charges. So sodium being in group 1, I'm just going to totally ditch sodium. So let's go through and let's check this out. It's going to be my HSO3. It's going to be the charge of negative. That's a bit of a weird looking negative. Let's fix that there. It's going to be aqueous. And of course, we're going to react that with water. So H2O liquid. So let's see. It does have an H in it, right? My hydrogen sulfide, actually, my hydrogen sulfite does have an H in it. So it's reasonable that that H would be given to the water, and I would form H3O plus. Cool. And if it gave it away, it'd be SO4. Keep saying SO4, SO3, 2 negative aqueous. And then we can do a quick check with this. Okay, did that make sense that it could give away a hydrogen? Yep, totally. H3O is produced, that's normal. SO3, 2 negative, is that a polyatomic ion? Is that something that's recognizable? Oh yeah, big time. So this, absolutely, that would work out. And if it works out this way, it is indeed an acid. Cool. Could it work the other way? This is something that's weird. This is why this one is tough. So HSO3, I keep wanting to say 2 negative, but it is not 2 negative. HSO3 negative plus H2O. If it were to become a base, one of the hydrogens would have to be given over here. So H plus, one of the hydrogens given that way. From the water to the HSO, geez, Murphy, 3. There we go. And if that happens, we'd end up with H2SO4, SO3. Oh man, I'm getting tired of this example. You probably are too. SO3, aqueous. Okay, let's do a quick check. OH, is that reasonable? Yeah. H2O giving a hydrogen away, is that reasonable? Oh yeah, that's no problem there. Is H2SO3 something that we've seen before? Totally. So in this case, this one could actually act as a base as well. So could act as an acid, could act as a base. That's a weird one. It definitely could be, and it does act as both. When you get to Chem 30, you'll learn a little bit more about when it acts like an acid and when it acts like a base. For now, know that it can do both. Cool. Okay. Just with this one, I kind of want to share something with you actually here. So it can act as an acid if it has an extra hydrogen. Right? Hopefully people have seen that a little bit. You got an extra hydrogen? Oh yeah, you could pretend that you could be an acid, absolutely. If it's got a negative space, that's a dead giveaway. So for example, HSO3 has a negative. I'm going to highlight in red over here. It has a negative. That's a space for another hydrogen. Those are 2 dead giveaways. It doesn't work perfectly all the time. So for example, NH3 way up here wouldn't work out perfectly, but that's a nice little shortcut, right? So if you kind of zoned out a little bit there, rewind for 30 seconds. I just gave you a good shortcut. Anyways, one last example. I'll tell you what to work on. I'm just going to clean some space up here. The barium oxide. So the metallic oxide is what we want to look at. Okay, got the right felt pen. So with this one, BaO, just like the other ones, the non-metallic oxides, we want a chemical reaction first and foremost. So I'm going to react that with water, H2O. And you'll notice that The oxides typically have, well, they don't dissociate as well, put it that way. So it's going to react with water, and it's going to produce, and we're just jamming everything together, BaOH2. Now, what's the charge on barium? If you're thinking to yourself, 2 plus, and what's the charge on hydroxide? 2 negative. You're absolutely spot on. And now look at what we've got here, BaOH2. Well, that's just a soluble ionic compound that contains hydroxide. So BaOH2 is just going to dissociate, simple as that, into barium ions plus hydroxide ions, and actually 2 of those hydroxides. So those ones are a little bit trickier for F. Still doable, but a little tiny bit trickier. Okay, last thing that I want to do with this, I'm just about done talking here, is go through and just kind of label. So question 1 and 2, fairly straightforward. You can go through and have a look at those ones. For the next page here, and actually, you know what I'm going to do? I'm not going to go through and label it because it's going to be a waste of your time. But practice, tell you what to practice, and I'll tell you what to do if you're having a bit of a hard time to start. So page 6 to 7, 8. So page 6 to 8. Go through and write them out. If you're getting confused, the first thing that I would check, and if you're having a hard time figuring out if it's acid-base, what it does, check answers on Google Classroom, but check answer for acid or base first. So just look, and it says, I'm looking at the answer key right now, to be honest with you, it says acid, 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 base, base, acid, base, acid, and it says it in brackets afterwards. So just check that first, and then from there, see if you can figure it out. And if you're still having trouble, look at the more detailed one, and obviously contact me. Anyways, that is it for today. It's a bit of a longer one. Make sure you're doing a bit of practice, and make sure you're checking in with me. Let me know how things are going. Anyways, that's it for now. See you later, Chem 20s.